The genetic component that would influence so much glycogen.
I mean, part of like naturally who holds, maybe have more substrate versus not is genetic, right? There are studies that show there are various components of like metabolism that individuals just have a genetic predisposition to maybe have more. Some of it is also like, well, if you have type 2 fibers, in general, they are more well suited to use glycogen for metabolism, right? So if you're an individual who has more type 2 fibers, chances are your muscles are going to have higher glycogen content because you have more of that fiber type that uses that substrate. Versus if you're an endurance athlete or more genetically type 1, they're great endurance athletes who are 70% type 1 muscle fibers. They're going to have a lot more lipid content, right? That's because type 1s are better at using lipids because they're more oxidative. Okay? But yes, absolutely, for sure. When we get to the aerobic training lecture, I'll mention a few studies where, sometimes they thought people were like blood doping, but he was a world champion and just had genetic abnormalities. Luckily, it was documented from his adolescence and childhood. He had doctors like doing these tests. It was proven he wasn't blood doping, but like totally genetic abnormality. That's why he had such high aerobic capacity because of his genetics. Right? It was totally natural. So, and then you can also do like carb loading, right? If you completely deplete, you work out really, really hard, completely deplete your glycogen, then you super compensate your diet with glycogen in a pretty rapid period of time, you can hold even more glycogen in your muscle, and that's carb loading. If you're familiar with that, right? So these are all cases where you can hold more of this substrate. You have more glycogen, more carbs in your muscle. You could do more anaerobic work, right? Potentially. Another substrate we use for exercise are lipids. Okay, we use fats, and so if we look here on this figure, on this image, these little white droplets, those are lipid droplets. Those are the fats we use during exercise, the stored form. Okay, so these lipid droplets contain triglycerides. Okay, triglycerides are the stored form of fat in the muscle and in adipose tissue. But we do not directly use lipids, we do not directly use triglycerides for energy. Okay? First, the triglyceride has to be broken apart. Right? A triglyceride is made up of a glycerol backbone and 3 fatty acid chains. Now, the fatty acids can, vary in any number of carbon units. You can have a 16 chain carbon fatty acid, 18, 21, right? So you can have any, or 18, you can have any variety length of, well, there is a range, right? It's not like you can have one, it's naturally not one, usually longer. But the idea is that these fatty acid chains are linked, they're bound to this glycerol molecule. In order for you to use these fatty acids, you have to first break them away from this glycerol molecule, okay? The enzyme that does that is a lipase, right? So the process of lipolysis is making those fatty acids free, right? You've heard of free fatty acids before, yes? Right? You use free fatty acids for energy during exercise. You don't use triglycerides. Right? Because triglycerides are still stored. But free fatty acids, you do use. Okay? Now, just a heads up, you don't want to confuse the terms lipolysis and beta oxidation. What's beta oxidation? The oxidation of those fatty acids. Okay? During beta oxidation, those fatty acids are being cleaved into 2 carbon unit pairs into acetyl-CoA. And then those acetyl-CoAs go to the Krebs cycle and blah, blah, electron transport chain. But on the exam, I have seen numerous times students confuse the terms lipolysis and beta oxidation. So while they get the process right, if they were to write it out on an essay, if you say, in lipolysis you're breaking down fatty acids into acetyl-CoA, that's incorrect, right? That's beta oxidation, right? The term you used was not right. So let's not confuse that. First, you have to undergo lipolysis, which is freeing those free fatty acids from the glycerol. Then those free fatty acids go to beta oxidation, where they're then cleaved and oxidized and turned to acetyl-CoA. Cool? Make sure you remember that. I'm telling you because on the exam, I use those terms quite a bit as we talk about substrates. I don't want you to get them wrong or confused. Now, we can use protein for energy, although it's not our preferred use substrate, okay? Proteins are made up of amino acids, right? Proteins are just a bunch of amino acids, linked together in tertiary and quaternary structures, okay? Some proteins, some amino acids can be used for energy more readily. So if we've heard of branched chain amino acids, like leucine, isoleucine, and valine, those are 3 branched chain amino acids that can be used for energy pretty readily, and it's not a bad thing. But for the most part of all the 20 essential amino acids, our muscle does not really want to use amino acids for energy because number one, protein is really valuable, right? It's not readily found in nature in high quantities, right? And also, like our structures in our bodies are made of protein, so we want to be able to keep that protein, and we would prefer to use carbohydrates and fats for energy. Now, we can use the protein for energy. First, we have to take the amino acid off of the carbon molecule on those proteins, and then we can turn it into carbon backbone that can be used in a way that's similar to glucose, right? It can enter glycolysis at various steps, or it can enter the Krebs cycle as a Krebs cycle intermediate, okay? But that process called deamination, that process requires oxygen. So you can't remove that nitrogen from that protein unless you have oxygen present, right? So again, we can't use proteins as a substrate for high intensity exercise because the nature of high intensity exercise is there's not enough oxygen. So we can't use proteins, we can't use fats during high intensity. We're only left with carbohydrates, okay? We can get the same caloric equivalent from carbohydrates and proteins, but again, breaking down protein to use for energy takes oxygen and it's a much longer process. And when we think about it realistically, because we would prefer to use other substrates besides proteins, the only cases we're going to use protein for energy is in cases where you are performing exercise in an energy depleted state, like a severe diet, right? An energy restricted diet. Starvation is a case where you're starting to use more energy from proteins, breaking down proteins, with a huge caloric deficit, or exercise that's longer than 3 hours. Okay. So if we can think about what most of us are exercising, like sustained exercise, so like let's go run and stuff, right? So most of us are not exercising continuously for 4 hours. So most caloric expenditure equations don't even include protein in their caloric expenditure because it's such a minuscule contribution to energy expenditure that it's really not necessary. Okay, but it does happen, and we think about practically. Someone's starving, someone goes on a crash diet. Yes, you lose fat mass, but you also lose a lot of muscle mass too. Why? Your body doesn't have enough calories. It needs glucose somewhere. It needs some of these intermediates from glycolysis to keep the Krebs cycle going. So what does it do? I'll take some carbons off of protein, get rid of the nitrogen, and now we have kind of a structure that we can sort of use like glucose to keep those processes going. And over time, you lose muscle mass, you atrophy. And that sucks, right? We don't want to do that. So, but that's practically, you can think about that, right? So yes, we do use proteins for energy, but under certain circumstances, and it's not likely for all of us that we would be using that during normal exercising conditions. Yes?
Is it like an efficient tool?
Not really, no, because number one, it requires oxygen and it takes a long time. So we're thinking about if you're going to get the same amount of calories from carbohydrates versus protein, you're better off. It's more efficient, more time efficient to get it from, and actually oxygen efficient to get it from carbohydrate versus proteins because one takes many, many more metabolic steps and oxygen, and the other one does not. So, and if we're thinking about, well, if we're going to use an oxidative pathway to make energy, well, then we actually get twice the amount of energy from fats than we would from the protein. So, in both situations, using proteins really wouldn't be the best case scenario. But we do, just in very special cases. So, but if you want to think about, if you look at these graphs, all these metabolic pathways, you start from carbs or protein, carbs, proteins, or fats, We are all starting from these big molecules, you know, carbohydrates or triglycerides or proteins, right? And we're breaking them down into the smaller units, and eventually they are broken down into a common molecule that can enter the Krebs cycle or directly or enter as a Krebs cycle intermediate. So these big, large molecules are broken down into smaller molecules where they eventually produce, you know, nitrogen, urea, carbon dioxide, and ATP. Okay, so that's essentially what we're doing. We can interchangeably use these substrates, but only in certain pathways that allow us to do so, like these oxidative pathways. We can't use fats up here because it's not really in a form or a structure, or the enzymes up here don't work with these substrates at that point. But the enzymes down here work with a substrate that fats and proteins and carbs can be turned into. Right? And that's where the common pathways converge. Make sense? Cool. So we'll talk about bioenergetics, okay? More specifically, those are the fuels we talked about. So bioenergetics essentially is the formation of ATP. We have a couple of pathways. We have the formation of ATP via phosphocreatine. Okay, we will see phosphocreatine abbreviated as PC, PCR, CP for creatine phosphate. There are all three abbreviations, phosphocreatine or creatine phosphate, they're all equivalent. Okay, so wherever you see CP or CPR or PCR or PC, it's phosphocreatine. We can also make ATP from the breakdown of glucose and glycogen by glycolysis, and then we can also produce ATP via oxidative phosphorylation. Okay, so aerobic pathways do not involve oxygen, hence anaerobic. Those two pathways are PCR breakdown and glycolysis. Aerobic pathways do require oxygen, and that is through oxidative phosphorylation. Okay? Why is it called oxidative phosphorylation? What's being phosphorylated? Oxygen's being phosphorylated? What's being phosphorylated? What are the products of the electron transport chain? ATP and water. So which of those molecules has a phosphate on it? ATP, right? But if ATP has the phosphate on it, then what must have been phosphorylated? ADP, right? So ADP was phosphorylated with the presence of oxygen. Right? So we synthesize ATP in the presence of oxygen via oxidative phosphorylation, right? Because the presence of oxygen allows ADP to be phosphorylated. That's where that word, those terms come from. This is different than anaerobic pathways. We don't call this oxidative phosphorylation because these don't require oxygen. These steps are through substrate level phosphorylation. Okay. This part down here we'll revisit again when we talk about aerobic metabolism, so I don't need to say it again, but substrate level phosphorylation I will say again, because when we think about what's a substrate, what do you mean by substrate level phosphorylation? It means we're literally taking a substrate that has a phosphate on it, taking the phosphate off of this substrate and putting it onto ADP. Okay, so substrate level phosphorylation means we're taking substrates that already have phosphates on them that are not ATP or ADP, ripping the phosphates off and putting it on ADP. Okay? So essentially, both these pathways involve phosphorylation of ADP into ATP. One process occurs with oxygen, oxidative phosphorylation. The other involves substrates that have phosphates, substrate level phosphorylation. Do you guys remember those terms from 346? Yeah. Okay. So ATP is a high energy bond, right? It is the currency of our cell. There's a lot of energy held in between the phosphates of ATP, like I already told you about. Imagine the spring. You release the spring, you're releasing the energy, the stored potential energy. Okay. Phosphocreatine or creatine phosphate is actually the energy held in the bond between creatine and phosphate, there's actually more energy there than compared to the bond, the energy in the bond between the phosphates of ATP. But can our cells directly use phosphocreatine for energy? To actually use them for energy? No. Practically, if we think about it, like you think about muscle contraction. You remember the cross-bridge cycling, right? Right, the sliding filament theory, right? The head of myosin. What's on the head of myosin that allows it to go through the cross-bridge cycle? A myosin ATPase. What does the ATPase do? Takes an ATP, hydrolyzes it. It's an enzyme, ATPase. It splits that ATP into an ADP and an inorganic phosphate. Now they're split. It's on the head of myosin. Now it gets back to the loaded position, power position, ready for another contraction cycle. Right? Let's go. It's in rigor. If there's ATP, goes back on. Hydrolysis from ATPase. Go. Charges, so on and so forth. Right? Remember that. Muscle contraction, the head of myosin does not have creatine kinase on the head of that myosin molecule. It can't go through cross-bridge cycling on the head of myosin with creatine kinase because there is no creatine kinase on the myosin head. There's an ATPase, right? So we can't use phosphocreatine directly for energy because that's not the currency that our cells use for energy, okay? It's like if you want to use euros here. You can't. You have to convert it to dollars first. If I want to use dollars in Europe, I can't. I got to convert those to euros. So that's kind of what's happening with these bioenergetic pathways. We know we have a valuable substrate that has the potential for a lot of energy, but we can't use it directly. So we've got to convert it into something that is usable, which is ATP. Okay? So yeah, the energy in the bond of phosphocreatine is actually higher than between the phosphates of ATP, but what we can do is we can split that energy from the phosphocreatine. That energy that's released, we can use that energy and that phosphate to resynthesize ATP. Remember this from 346? Okay. So if you look here, what's the only difference between phosphocreatine and creatine? There's a phosphate here. That's the only difference, okay? So if you have a creatine phosphate plus an ADP and a hydrogen ion, with the presence of creatine kinase, you can resynthesize ATP, right? You take the phosphate off of creatine phosphate, put it onto the ADP, now you make ATP, and now there's no more phosphate there, so you just have a creatine. The enzyme that catalyzes this reaction is creatine kinase. This is the rate limiting enzyme of that step, of this pathway. Creatine kinase is the rate limiting enzyme of the phosphocreatine system. Okay? Got it? So, if we look at what happens during high intensity efforts or a sprint, so this is an all-out maximal effort sprint, we look at the amount of ATP in the muscle and the presence of phosphocreatine during sprinting. The start of the sprint, we have high ATP in our muscle, but notice as we start sprinting, this is all-out max activity, the amount of ATP starts to decrease. Notice as ATP starts to decrease, we see a rapid drop in PCR. But the drop in PCR maintains intracellular ATP. Right? The purpose of phosphocreatine is to supply an energy source, a substrate, to resynthesize ATP. So once we start using ATP, phosphocreatine is now activated from the creatine kinase and starts ripping off the phosphates and putting that back onto ADP. Right? As long as you have phosphocreatine, you can keep maintaining ATP availability. But notice when you run out or deplete your phosphocreatine, you can't maintain that ATP. If you don't maintain the ATP, your muscles can't keep contracting at the same rate. So what happens? You slow down and reach exhaustion. Right? Okay? So, This process happens because creatine kinase facilitates that reaction, okay? Creatine kinase is stimulated by the drop in ATP, the increase in ADP, and the increase in inorganic phosphate. Right? Again, if we have ATP to start, and now we start seeing an increase in ADP and inorganic phosphate, where is that coming from? Breaking down the ATP, right? So how does creatine kinase know, oh, I have to start breaking down phosphocreatine, because the ADP and inorganic phosphate are telling that enzyme you're breaking down ATP. So now you can turn on and start making more ATP with it, right?
Can you repeat what's
The ADP and the inorganic phosphate, when those increase, it stimulates the creatine kinase to become more active. Also, the drop in ATP also stimulates the creatine kinase. Right? They're kind of reciprocal. Now, if we remember glycolysis, right? Can we just start using glycolysis right away? If we do an all-out effort, about how long does it take before we start kicking into glycolysis? Time-wise. Yeah, usually 15 to 30 seconds, kind of around there, right? Right after around 15 seconds, we're really getting into glycolysis, and 30 seconds it's full tilt, right? So, why can't we just kick into glycolysis right away? First, right? First we converted G6B, but then have we made ATP yet? No. What do we got to do next? PFK gets turned on, right? Have we made an ATP yet there? No. PFK uses another ATP. Then we split that in half, goes through the rest of glycolysis, then we make ATP, right? So there's way more steps in glycolysis that need to happen before we can make ATP. And the key factor is, first, you have to turn on PFK, which is a rate-limiting enzyme. The reason I'm saying this because why can we, if I wanted to, I can just sprint right now, sprint for as long as I want, right away. There's no limiting factor. I don't need to wait to turn on creatine kinase to access these oxygen to resynthesize ATP. The reason there's no lag time, why is the phosphagen system called the immediate energy system? Because creatine kinase is already at high activity in your muscles. You don't need to increase the activity of creatine kinase so much more to ramp up that signal, because right now it's already very, very high. So if I wanted to go for a sprint right away, ATP turnover is already going and resynthesizing because the creatine kinase is already high. But when you start breaking down the ATP, and the ADP and inorganic phosphate go up, those stimulate creatine kinase to be even higher, right? So if the activity of creatine kinase is already high, and ATP breakdown increases it even more, that allows us to use all of our immediate energy right away, right now, no waiting. PFK activity at rest, this activity is very low. So we can't just go right into glycolysis because all the things that keep PFK off, they're still there until we've exhausted phosphocreatine, or we've broken down enough ATP to then turn on PFK, right? What turns on PFK? AMP, ADP, the decrease in ATP, the drop in phosphocreatine, right? What turns on PFK? More creatine, more inorganic phosphate. If there's a lot of phosphocreatine together, that keeps PFK off, right? You can't just jump right into glycolysis if it's max effort, unless you first depleted your phosphocreatine, and then we go into glycolysis. Does that make sense? Okay. So that's why it's the immediate energy system, because this enzyme, its activity is already very high. And remember we said, enzymes facilitate reactions, they facilitate things to occur, to happen readily. Okay, so the reason why we can resynthesize ATP very quickly with phosphocreatine is because the enzyme activity of creatine kinase is already very high, and it can increase even further with max intensity. Glycolysis, PFK is low. Is that clear? So I say this because I can't tell you how often when I give examples on exam of like intensity of effort and duration, time duration, and I say which is the metabolic pathway that's most likely to be used, or which substrate is more likely to be maximally used in these time frames, people get all confused because they're like, oh, well, we're going to use, it's 10 seconds, okay, that's high intensity, it's anaerobic, it's got to be carbohydrates, glycolysis. No, right? Glycolysis doesn't turn on if it's max intensity until we've depleted enough CCl. Then it's glycolysis, right? So in that time frame, 100% max, 10 seconds, not glycolysis yet, right? Does that make sense? So make sure you know those time and intensity kind of things, because we shift between energy systems to maintain intracellular ATP the best we can, given the intensity. Cool? All right. So now we talked about how we use phosphocreatine, but how do we remake it? Okay, so in this image, I'll walk you through it. The myofibrils, this is where the sarcomeres are using ATP, right? So actin and myosin, or myosin specifically, is using ATP to go through the power stroke. So we have ATP in the cell. The cross-bridge cycling uses the ATP. Now we produce an ADP. What happens? There's more ADP. Creatine kinase senses that. It takes phosphocreatine, uses that energy and the phosphate to put that back onto ADP and resynthesize ATP. Now we have an ATP to do more work, but we have a creatine, right? And we will continue to do this until that entire effort has finished, until we've reached exhaustion, or we've finished the sprint, or the repetitions, or whatever, right? After that high intensity effort, now we have a bunch of creatine, okay? That creatine is then shuttled into the mitochondria where there's a lot of ATP, okay? There's a mitochondrial creatine kinase that takes the phosphate off of ATP, puts it back onto creatine, resynthesizes phosphocreatine, and sends it back out to the cellular fiber. This concept's on your exam. Okay? I know it's like, well, I know you learn in 346 about how you use phosphocreatine, but probably don't learn how you resynthesize it. Okay? This is how. So we use ATP, we use phosphocreatine anaerobically. We resynthesize it aerobically, or oxidatively. So, what I love about exercise is a lot of times you can just think about like a time you've exercised or done some kind of that type of effort and think, well, what happened to me when I was in that situation? Okay? Who's ever done lots of really intense running or sprinting, and the coach or somebody, you weren't totally finished yet, but you had to run again. They made you run again. Could you do as much work as before? No, right? Why couldn't you do as much? Why couldn't you run as fast or run as far as the first time?
Because your PCR is depleted.
It's depleted relative to the first time, right? Depleted relative to your full recovery, right? If you had rest, in that resting period, you repleted some, but not your maximum, right? So if you had to do another all-out effort, you would still give full effort, but the work performed would be less. Why? Because you don't have enough of the substrate to do that extra work that you did before, because you didn't fully recover. So practically, if you think, are you fully recovered? Well, yeah, I feel pretty recovered. You can most likely, with longer recovery periods, do the same amount of work, right? At some point, if you do 10 sprints, residual fatigue comes in, you know, calcium's not handled the same way, motor units function differently. That is like systematic fatigue, which is different than like the substrate available now. But we know that if you have enough recovery period in between high intensity efforts, you can maintain high intensity or high work output every time you do an effort, as long as you have enough recovery. You don't have enough recovery, you can't run as fast, you can't run as long, you can't do as many reps. Why? Because you're still fatigued, because you don't have enough of the substrate recovered yet. Does that make sense? So this process, you can think about like, okay, I just spent, okay, all this extra breathing. Why are we breathing so much? Because we need that oxygen to go to the mitochondria to resynthesize the phosphocreatine, right? We used all that phosphocreatine anaerobically, but when we're done, we consume a lot of oxygen at rest to resynthesize the phosphocreatine in recovery. That's what I mean by it's resynthesized oxidatively. And how do we know this? How do we know that it's synthesized? Besides practically, you think, oh, well, yeah, you have rest periods, it just recovers, right? Well, no. I show a lot of studies in this class. In this study, they had them do knee extensions to failure, but they had 3 different recovery protocols, right? So they did as many knee extensions as possible, and they looked at the amount of phosphocreatine in the muscle before the effort, at the very end of the effort, and then several minutes into recovery. What we see is that when you do all-out intensity knee extensions to failure, the amount of phosphocreatine in the muscle drops very low. We would expect that. That's what the purpose of that is immediate. It's anaerobic. But when we have blood flow intact, if we have enough recovery time, notice how the amount of phosphocreatine returns to about baseline, just kind of around baseline levels, right around somewhere between 4 and 8 minutes. We're still not exactly at baseline, but within the margin of error, right around, around 4 minutes here, right? We're kind of near where we were to start. So it took about 4 minutes or 5 minutes to get close to our pre-exercise phosphocreatine levels. Who's taken 417 before? Taking now, right? What are the recommendations if you're training for maximum strength and power? What are the recommended rest intervals between sets? 3 to 5 minutes, yes. Where do those recommendations come from? Obviously, you could do as many sets, test as many people as possible, and you would probably collect data and see, oh, it probably takes people around 3 to 5 minutes, more or less. But we can scientifically measure the required amount, because if you look at the actual substrate needed during power and strength exercise, they needed 3 to 5 minutes at least. In some cases, up to 8 to fully recover phosphocreatine. Right? And think about it. You do reps in the weight room, you just did it to failure, you give yourself 30 seconds rest, you cannot do the same number of reps before. You are still fatigued. You will not do the same number of reps. You wait 3 minutes, 4 minutes, 10 minutes, you're dialing on your phone, get off, it's my equipment, I need to use it, right? People's rushing you in. You got plenty of reps, right? You do more reps. So practically we know it makes sense. But what happens when we had a recovery where blood flow was not totally intact, like an isometric contraction, right? So in this case, they had to hold their thigh isometrically against resistance. They weren't contracting, but they were just holding it there for the recovery period. They still recovered phosphocreatine, but it was not as much as the blood flow intact condition, right? Why was that? Because remember, when you contract your muscles, there's a skeletal muscle pump that allows blood flow to go through, it returns to the heart, it circulates, and all that kind of stuff, right? Also, the fact that you're continuously contracting your muscle, they're still using ATP and phosphocreatine, right? So you're not totally going to resynthesize all of it because of both those factors. But what happens when you totally occlude the leg? So they put a tourniquet around the leg and they totally occluded blood flow from that limb. There was no phosphocreatine resynthesized at all in recovery. So literally, if you have no oxygenated blood going to that limb in recovery, you made no phosphocreatine. What does oxygenated blood have to do with phosphocreatine? The blood carries the oxygen, but where does that go?
That's not good.
To the mitochondria, right? It's in the mitochondria, you make ATP, that ATP resynthesizes phosphocreatine, right? So this proves that, yes, this is the mechanism that allows us to resynthesize phosphocreatine, oxygen, right? Oxygen must be present to resynthesize this anaerobic substrate used during high intensity exercise, okay? This concept's on your exam, I promise you. I asked it a couple different ways, so make sure you know this concept. All right, we'll talk here too about, we talked a lot of this class about cell signaling molecules, right? And cell signaling molecules are proteins and enzymes inside the muscle that stimulate adaptations, okay? Respond to an exercise stimuli or an exercise thing is happening during exercise, and then it will turn on and regulate an adaptation later on. So in this study, they had individuals do 4 30-second sprints on a cycle. They took a biopsy, a muscle biopsy at rest, after the first sprint, after the 4th sprint, and 3 hours later in recovery. And what do we see? At rest, here's ATP. After the first sprint, ATP was not different than rest. But we did decrease phosphocreatine. What's the purpose of phosphocreatine? To maintain intracellular ATP, right? So phosphocreatine went down, but cellular ATP stayed the same, statistically speaking. If we break down phosphocreatine, we increase creatine. That makes sense. Well, after the 4th sprint, ATP was significantly decreased. Okay, so this shows that after repeated bouts, right, at some point it becomes harder for the muscle to maintain that intracellular ATP, right? This relates to even if there's enough rest, you can have as much rest in between sessions, at some point your work output is not going to be efficacious, right? You could do 5 sprints, 10 sprints, 20 sprints, doesn't matter how many rest in between each of those sprints, you are going to not have the same work output as the first one, even if because you can't maintain cellular ATP the same way. Now notice, even after the first sprint, we still decreased muscle glycogen, right? So the first sprint, we used phosphocreatine, we used glycogen, but we still maintained intracellular ATP. By the 4th sprint, we still had used glycogen, we still used phosphocreatine, and ATP had decreased. It was the 4th 30-second sprint. Now notice that here's an enzyme called AMPK. If you see this protein, if it has any protein that has a P in front of it, it means phosphorylated. So AMPK is a protein that senses how much energy is in the cell. What does our cell think is energy? What does our cell use for energy? ATP. So notice that phosphocreatine decreased after the first sprint, but AMPK didn't turn on. AMP decreased after the 4th sprint, and then AMPK turned on, right? So if here's a protein that senses this amount of energy in the cell, when ATP goes down, then it'll turn on. Now it's going to do stuff, okay, to help recovery. Why do I bring up AMPK? Because AMPK is involved in a pathway that helps you make more mitochondria. It senses how much energy is present or how much energy is used. If there's low energy in the cell, AMPK turns on during exercise, and then in recovery, it helps stimulate you making more mitochondria. So the next time you exercise, or the next 4 times you exercise, if you have more mitochondria, are you going to be able to make more ATP? Does that make exercise easier next time? Is that adaptation? Yes. Adaptations happen because these cellular stresses, like a decrease in ATP, like a decrease in glycogen, turn on these cell signaling proteins, and then they turn on transcription factors, gene responses that make protein synthesis happen to produce an adaptation later. And that adaptation makes that exercise stimulus a little easier. Yes.
So without ATP depletion, you wouldn't get AMPK.
AMPK, it could decrease because of, AMPK could turn on because of a decrease in glycogen. So glycogen is also energy in the muscle. So if glycogen decreases, that would also increase AMPK as well, right? Because this protein senses what energy is available. Is it there or is it not? If it's not, then I'll turn on. If it's ATP or glycogen, both of those would indicate there's not enough energy available. Make sense? Yes.
Since this guy's going all out, and you only can do so much beta oxidation for like fat, would it, if that was calculated on the graph, would it just be like a consistent value?
Oh, there would be zero fat here. Right. You can only use fats for energy with the presence of oxygen. What do you think? Like, you're doing all-out intensity of effort, right? You're still breathing, but it's not enough oxygen for the amount of work you're doing, right? So if you're performing this much work, but the amount of oxygen you're consuming to do this much work is only this much, then all that ATP must be coming from anaerobic sources, right? But if you lower the intensity, now you're using this much ATP, but you're consuming this much oxygen. Well, now this oxygen can be used with fats to make up that ATP, right? So in 30 seconds, it's not enough time or oxygen to stimulate fat usage, right? Which is why we don't use fats. Typically take, aerobic metabolism doesn't take in until at least 3 to 5 minutes. And fats are even longer, 20 minutes or so. But make a good concept, because we talk about cell signaling all semester. So this is kind of our first introduction to it. But ultimately, why does creatine work? Because creatine, like we just mentioned, creatine gives you more substrate to resynthesize ATP so you can do more work, okay? When you supplement with creatine, when you take creatine, it joins and bonds with the inorganic phosphates floating around in your muscle. So I'm a creatine, oh, I need a phosphate. Oh, there you are. Now I'm phosphocreatine. So the more you load your muscle with creatine, the more phosphocreatine you make. Now you have more pre-exercise phosphocreatine. Right? So now, if you were to do a high-intensity sprint or a high-intensity effort, you have more phosphocreatine to do a longer sprint, to do more reps, to be a faster, more mean work capacity. Okay? And over time, more work means more adaptations. And why do I say this? Because they've done studies in humans and in mice and rats and rodents. When you have a placebo group and a creatine group do the exact same amount of sets and reps, there's no difference between adaptations. They both get just as strong and just as big. But when you let both groups do as many as they can do, over 6 to 12 weeks, the creatine group starts doing more reps every set. And over every set, every workout, every week, that results in way more volume compared to placebo group. And the more volume results in better adaptations. So creatine only works if you use it how it's intended to do, which is to do more work. Work. When's that album coming? Jeez. Right, so the idea is that creatine lets you do more work, and that's the benefit of it. People will say, oh, creatine is not effective. Creatine, creatine is one of the most effective and scientifically proven ergogenic aids out there. Creatine, caffeine, and whey protein, I will die on that hill for those three, for sure. Most scientifically proven. There is truth. Why doesn't creatine work for everyone? Because some people already have a lot of phosphocreatine in their muscle to begin with. So just genetically. So supplementing with more creatine isn't really going to top it up that much more. Or if your diet already has a lot of red meat, which is where creatine comes from, supplementing with more creatine is not going to do it for you. Not going to make much of a difference. But think about a population like vegans and vegetarians. They have shown studies where they don't consume red meat, right? So their diet is deficient in creatine. So when you give vegans and vegetarians creatine, they see a huge increase in performance and adaptation because they don't have that substrate in their diet. And when supplementing improves the adaptations. So creatine doesn't work for everybody because it does work for most people, but there are conditions where, maybe just genetically or it's in your diet or so on and so forth. But scientifically, creatine works because it lets you do more work. And if you train in a way that lets you do more work, you do get more adaptations, right? If you're totally untrained, don't bank on all your adaptations coming from creatine. the best stimulus is the lifting. Lift for a few months, maybe a year or two, then get into creatine, right? Once you kind of hit some of the window of the newness, right? But creatine is effective at enhancing adaptations. You just have to use it the right way, at the right time, and things like that, all right? And what are some of the mechanisms? Well, like we said, more pre-exercise creatine available, more work output. It delays the depletion of creatine. It means you can do more during the single high intensity effort bout. So overall performance increases in that singular bout, which means that the training intensity is higher. Not only is pre-exercise availability of phosphocreatine better, but it also, if you have more creatine in your muscle, you can resynthesize more in between each effort, right? So in between each sprint, you can recover it faster and have more. So that makes the workout quality even better, because now all your sprints are even more and being recovered faster compared to not having that creatine from before. Does that make sense? So it's the ability to do more work, yes.
So if you stop taking the creatine, do you still keep those adaptations?
For the most part, yes, you do. So you should take creatine for a few months, and then you can stop taking it. You know, it gets into your muscle, and it helps stay there. You go on a lower dose, you continue to take it, and then you change your training program, and you keep taking it at that point. Then you can go on again in a few months. Yes.
If your goal of like your workout would be to turn on okay, would taking creatine kind of mean you need to do more stress that point?
Well, we'll get about this we'll get into that a little bit later in some other lectures, but realistically, we don't want to train in a way to turn on any specific protein, only because the proteins are responding to stress. So whether that stress is a lot of metabolic stress, or low energy, or low oxygen, or heavy loads, or muscle damage, or hormones, right? They're going to turn on in a variety of different ways and in different combinations. So we can look at these cell-signaling proteins and say, hey, if there's a lot of proteins on at the same time, that was probably a stressful workout, right? But that's going to mean they're going to lead to a bunch of these types of adaptations, and we know that's probably a pretty good quality workout. And also keep in mind, over time, the proteins become desensitized. So they're not always going to turn on the same way, because if the point of the protein is to make an adaptation, once you have the adaptation, it doesn't need to turn on, right? So you actually hope it, keep trying to turn on this protein while you're already trained, so it's kind of desensitized, right? Or you change your training program to a very different training program, and then they turn on again. We'll cover that in a few other lectures there too. All right, so that's what we got on that. So we'll cover a little bit of glycogen, and yeah. All right, so like I had mentioned before, right, glycolysis, we produce ATP, but we have to invest ATP to start, okay? So in glycolysis, there's an energy investment phase where we invest 2 ATP, and then once we've invested those ATP, we can produce 4 ATP, okay? So the end of glycolysis, we produce the 4 ATP, which means our net ATP is either 2 or 3, depending on what we started with. And then we have NADH and pyruvates are also byproducts. So when we bring glucose into the cell, that process uses an ATP. Okay, so we use 1 ATP here to bring glucose into the cell. That gives us glucose 6-phosphate. Then the step with PFK uses another ATP to add another phosphate to that molecule, and then we split that molecule in half. And we produce 2 ATPs with this half and 2 ATPs with this half. So there's 2 investment up here, but there's production of 4 down here, meaning our net is going to be 2, or if we start with glycogen, the net will be 3. Okay? So with glycolysis, G6P is produced from 2 sources, from either blood glucose when it's brought into the cell, or from glucose that's already in the muscle, stored as glycogen. Okay? The glucose gets into the cell through protein transporters called glucophore proteins. Right? Glucophores actually transport glucose into the cells. And why do we care about this? Because, well, one, if we remember insulin, what is the function of insulin? Right? What does insulin do? decreases blood sugar, right? So when blood sugar is high, insulin's secreted to lower blood sugar. What does insulin do? Insulin binds to an insulin receptor, and then it tells a vesicle that has this GLUT4 transporter on it. It then tells this vesicle to move to the cell membrane and open up the floodgates and let glucose into the cell, right? So how does insulin work? It signals to the vesicles that contain the GLUT4s to actually uptake glucose into the cell. So if I asked you on an exam, is insulin the molecule that transports glucose into the cell? Is that true or false? That's false. Insulin is not the molecule. It signals, but it's not the molecule. The molecule that brings glucose in the cell is a GLUT4 transport protein. Okay? Now, why do we care about this? Because contraction can also stimulate those GLUT4s to turn on and increase glucose uptake. Let me ask you, during exercise, what's the insulin response during exercise? It goes down. Why does it go down? Glucagon goes up. Glucagon does go up, right? But they work in opposition, but they're working in opposition to what signals, right?
Yeah,
Well, if we're exercising, we're using glucose in the muscle, right? So we need more glucose. Insulin is a hormone that should bring glucose into the muscle, but actually it's going down. So how do we get glucose in the muscle? Hexokinase is the enzyme that is phosphorylation. It keeps it there. But the GLUT4s actually get turned on from contraction, right? So epinephrine actually antagonizes, it opposes, it suppresses, it blunts. They all mean the same thing. Epinephrine suppresses the insulin response. Epinephrine is our exercise hormone. Epinephrine makes us stronger, faster heart rates, vasodilation, more oxygen increases, right? Better calcium handling, mobilizing substrates. Epinephrine is everything to us in exercise. Okay? So the fact that epinephrine increases is good. It helps us sustain or resist this exercise session, but it suppresses insulin. So, oh man, how do we get insulin? How do we get glucose into the cell now if we don't have insulin? Muscle contraction brings that glucose in. But let me tell you this. Do all your cells have insulin receptors on them? Do you think? Do all your cells need glucose? Yeah, almost all your cells need them, right? Almost all your cells have insulin receptors, right? To my knowledge, they all do. Okay? So when insulin interacts with its receptor, it causes the reaction to increase glucose uptake. What if I was exercising and I get an insulin response and I'm running, right? So my legs, I don't know like that. My legs need the glucose, but insulin's released, and now I'm getting glucose uptake in my arms and my back and my shoulders. Do I need the glucose there? No, I need the glucose here, right? So in fact, if our insulin went up during exercise, it would actually cause glucose uptake in all the tissues, where all our receptors are, when we actually need the glucose in the exercising muscles, right? So the fact that insulin goes down, but muscle contraction stimulates glucose uptake in these muscles, this means that I get glucose uptake in these muscles that are contracting and not these muscles that are not contracting. It's actually pretty good, right? So it kind of suits both things. This is also why it's recommended diabetics to exercise. You can improve your glucose handling and glucose kinetics for up to 48 to 72 hours because the muscle is still sensitive from contracting and those GLUT4s are still responsive. And if you're diabetic, you're either insulin insensitive or you're insulin dependent, meaning you don't produce any insulin, right? So one way of mediating blood glucose would be to have chronically exercising, okay? Keeps your muscle still sensitive to take that glucose. Make sense? So once that glucose is in the cell, after those GLUT4s, there's an enzyme called hexokinase that uses an ATP to phosphorylate that glucose to form glucose 6-phosphate. And why do we care about this? Because when glucose is phosphorylated, it cannot leave the cell. It's trapped. Have you ever heard, oh, the muscle secreted glucose? You ever heard that? Have you heard the liver release glucose? Yes, because the liver has an enzyme to take the phosphate off, so now glucose can go. The muscle does not have that enzyme. So once the glucose goes into the muscle, it's phosphorylated, and now it has to stay there. So that first step of glycolysis, that first reaction, is by this enzyme called hexokinase. Hexokinase phosphorylates glucose to form glucose 6-phosphate. And that negatively charged molecule keeps and traps glucose in the cell, and this reaction is irreversible. Right. Now, mind you, I will never ask you to draw out figures or label figures, but if you should understand the concept of this figure. And what's happening here? Here's glucose, you have an ATP, here's hexokinase, the arrow goes this way, but not all the way this way, so this means that it uses an ATP to add a phosphate to this molecule. Here's the phosphate on the 6 carbon. Why is it called glucose 6-phosphate? Because 1, 2, 3, 4, 5, 6 carbon, where the phosphate's located. Cool? That's where we'll leave today. Okay? So, we'll pick up on this one next class. But yes, right, so we're going to talk about hexokinase quite a few more times. We talk about glycogen phosphorylase a lot. We will talk about glycogen phosphorylase and at least 2 to 3 other lectures in this unit. So make sure you know if you had this in ahead, glycogen phosphorylase is the one to look at. Make sure you kind of get a little understanding.